Okay, as you can see, I have skipped quite a few slides, mainly talking about D'Alembert's principle. As I've said, maybe I've been a little bit overambitious in preparing this course, so I will skip all these slides. They are there for your information, and go to the first formulation of the Lagrange equation. So remember that we have a system with n particles, right? So if there are no constraints, you have 3n equations, but you also have k constraints. So this means that you will have 3n minus k equations, right? So we've seen previously that it's a good idea to choose generalized coordinates, right? And these will go from q1 to q3n minus k, right? And in this equation, k is the kinetic energy. As you can see, there are 3n minus k equations, right? Because you write the equation for every j from 1 to 3n minus k. There is this term over here, which depends on the forces, the external forces, not only the external forces, but all forces that are applied on particle I. Okay, so these are the forces applied to particle I, and R here, Ri, is the position vector of particle I, and as we have seen before, you can write it in terms of all the generalized coordinates, right, from q1 to q3n minus k. So now you have the definition of this one, and of course you can take partial derivatives and compute this thing here, that is the generalized force. If you then write the kinetic energy and you apply this equation here, well, you end up with 3n minus k differential equations that are describing the system. Okay, let us apply this on this very simple system of a mass on an inclined plane. It's actually a mass spring damper system, as you can see, and we've seen previously that the motion of this mass can be described in terms of the generalized coordinate q, since we have only 1 degree of freedom. This Lagrangian first formulation will involve the kinetic energy, right? And in this case, the kinetic energy will be 1/2 m q dot squared. Okay, let's go a little bit further. So I've put here the equation of the first formulation of Lagrange. Since you have only one mass, okay, well, you have only one Lagrange equation, right? And so we have already written the kinetic energy of the system, and in this first slide I will stick to this left term of the equation. Right, this one is quite easy, as k, the kinetic energy, does not depend on q. Of course, this term here will not give any contribution. It's a 0 over here. Then we have this thing here. It's a derivative, the partial derivative of the kinetic energy with respect to q dot. So you have to see q dot as a variable, right? So if you see it as a variable, well, you will have a half times 2 times m q dot, which gives you m q dots. Sometimes in exercises I see the mistake that some people put here q double dots, but this thing here has to be seen as a derivative of kinetic energy with respect to the variable q dot. So indeed the result is this thing here. So now I have to take this thing here and take the time derivative, and of course this is easy. You obtain m q double dot, right? Okay, so we have arrived at this equation, right? This is the one that we've computed in the previous slide using the left hand side of the first formulation of Lagrange, and what we need is to determine Q, the generalized force. In the general formula there is a sum over here over all particles, but there is only one body here, it's the mass, so you end up with one element over here. This is the net force acting on the mass. R is the position vector, and you know that there is a relation between the position vector and the generalized coordinates, right? And so this is the partial derivative of this position vector with respect to the generalized coordinates. Okay, so let's try and draw our mass on an incline, right? So this is my mass here. Now comes the difficult part, drawing a spring, right? It has stiffness constant K, and then we have here a damper. Okay, see, that doesn't look too bad. And then we'll draw Y, and then we have our generalized coordinate Q, right? So if you look at it, the position vector xy can be written as a function of the generalized coordinate that gives my position vector, right? So we can kind of compute this one very easily. And now we have to look at all the forces that are acting on the system, and we see that there are three forces. Of course, there is gravity, yeah, there is the spring force, and there is the damping force, right? So we have to compute this thing here for these three forces. So this will give me three terms: a generalized force that is linked to the gravity force, qk here, generalized force linked to the spring force, and then qc here, which is the general force linked to the damping force. Okay, let us now compute these generalized forces. Remember that we had the position vector r, which is q cos theta minus q sine theta. If you take partial derivative, it's kind of easy to see that you have this thing here over here. So I'll draw again my system as best as I can. We have here the mass, we have the spring of stiffness K. We have the damper here, damping coefficient C. Yes, we know that we have an angle theta of the incline, right? So now I'm going to draw my system of coordinates, right? X and Y, and here the generalized coordinate Q. Okay, let us now look at all the forces that are acting on the system, and remember that you have gravity. Okay, gravity, it's a vector and it can be written like that. It's acting in the minus y direction, right? And then you have here the spring force, that is Fk, right? And it can be written like that. Yeah, see that in the x direction, of course, it's negative, right? And it's linked to the cosine, yeah. And in the y direction, it's positive, so it's linked here to this thing here. And you see, and the trick, the usual trick to see if you have not made any mistakes for sine or cosine, is to let the angle go to 0, and then of course you see that you should have something that is only in the minus x direction, and that should be minus kq. Okay, so this is indeed correct. So now we can compute our generalized gravitation force. So it's this one, scalar product with this one, and this will give you this result. And we can do the same for the general force associated with the spring force. This is your spring force here. You do the scalar product with this thing here, yeah, and you obtain this contribution. For the damping force, we have something very similar. Okay, the damping force, well, it's oriented in the same direction as the spring force. Yeah, so if you do the calculations, you'll have something that is like that. So this is what we had computed with the left hand side of this first Lagrangian formulation, right? And then it's equal to the sum of the generalized forces, right? So if you bring these terms on the other side, right, you end up with this equation. Remember, this one is written over here. This one is minus kq, and this one was mj sine theta. So we have the description of our mass spring damper system on an inclined plane. So this is the equation that we had found previously. If we look at the steady state solution, okay, steady state means that Q becomes constant. Well, you know that for the steady state, we'll have this term that goes away and this term that goes away. So if you compute Q, and I've denoted infinite here, at time that goes to an infinite value, then you bring this one to the other side and you divide by k, and you have the what is called a steady state solution. And what is often done is to write Q as the steady state solution plus some variation here. If you take the derivative, of course this one will not be contributing. Q dot is equal to dq dot, and Q double dot is equal to dq double dot. If you inject it in here, these two things here, you end up with this thing here, and this is the general form of a harmonic oscillator. And what you see here is the natural frequency squared, right? Okay, so now we arrive at the second formulation of the equation of Lagrange, and it's probably the one that you see most often. You remember that in the first formulation we had only kinetic energy coming into play. In this formulation also the potential energy will come in, and you remember that some forces that we call conservative, right, they can be written as be derivable from a potential function, so as minus the gradient of some potential function, yes. And in our example of the inclined mass, we will see that there will be two examples. Well, there is the spring force, and I think we had called this Fk, and there will be the gravitation force. Yeah. So if you use the potential energy in this Lagrangian, right, for the rest, well, what's happening here is exactly the same, right? We had 3n equations if the system is not constrained, but there are k constraints coming in, right? So you will have 3n minus k differential equations. We are working with generalized coordinates from q1 to q3n minus k. Okay, so this is why we have 3n minus k examples as j goes from 1 to 3n minus k. Okay, so if we use this potential energy over here, this means that in the generalized force we will have to consider only forces not arising from a potential. Yeah? And in our example of the mass and the spring mass system on an inclined plane, there is only one force that is not coming or arising from a potential, and this is the frictional force. In other examples, there might be other forces that are not arising from a potential, for instance, external forces, right? So in here, qj is this thing here as before. You have to sum over all particles, right? And these are the net forces on acting on particle I. This is again the position vector of particle I. But now you only have to do this for forces that are not arising from a potential. Why? Because the other forces, they will be covered using this potential function. So let us return to our example here. Remember that the position vector r is q cosine theta and minus q sine theta. We had already written the kinetic energy, and that was a half m q dot squared, and we can now write the potential energy, right? Well, there is potential energy stored in the spring, and this is a half q squared times k, and we have also potential energy from gravity, and this is mg, and you have to look at the height, and it's y here, and this y we see that it is minus q sine theta. So the potential energy is a half k q square minus mj q sine theta. Okay, so these ones will be used in the second formulation of Lagrange. Okay, so we had written the kinetic energy, we had written down the potential energy, and the Lagrangian is simply kinetic energy minus potential energy. So a very complicated computation gives you this result. Okay, so this is the second formulation of Lagrange's equation, right? So what we will need here is the Lagrangian, right? So the Lagrangian was k minus u, and here it's 1/2 mq dot squared minus 1/2 k q squared plus mj q sine theta, right? So now we can do the math. Oh, so Q, this is the generalized force. Remember, we have only one body over here, so we'll have, in this sum there will only be one term. There are no external forces, so the only force that is not arising from a potential is the frictional damping force. Okay, this QC, this one we had already computed previously, and it's minus CQ dot. Okay, so this one is equal to QC, and we have it over here. So now we do the derivative of the Lagrangian with respect to Q. This is Q dot, will not give any contribution. We take the derivative of this one. This is minus KQ, and here we do the derivative with respect to Q, and this mg sine theta, right? So this is this term that we've computed. Now we're going to compute this one. Okay, don't forget that we have to see here in this computation Q dot as a variable. This will not be giving a contribution, and the same here, this will not be giving a contribution. The only contribution comes from this term, and we had already done that, and this gives you then mq dot. Then when you have computed this thing here, you need to compute this thing here, and this is what is done over here, right? And this gives you mq double dot. Mq double dot, that's this term here, minus this one, okay, gives you plus kq minus mg sine theta equals qc, and you take it to the other side and you obtain this equation. And without being surprised, it's exactly the same to what we had obtained, of course, with the first formulation of Lagrange. Maybe that it's a little bit easier to compute and to work with this Lagrangian, as we have fewer generalized forces to compute. Okay, you've seen that in the second formulation of Lagrange, well, in the generalized forces, you had only two types of forces that were not accounted for by forces deriving from a potential. These were frictional forces and external forces. In this Lagrangian third formulation, we are trying to put only external forces into the generalized force, and this works for frictional forces that are, well, very frequently used in examples. They are proportional to the velocity of the particle. Remember that the velocity is a vector, so if you take, for instance, the x component, you have that the force is minus kx times the speed in the x component. If your force has this form, then you can use what is called Rayleigh's dissipation function, which is constructed like that, sorry. Here again, it's a summation over all particles. In general, you have n particles, and then the frictional forces can be obtained using the gradient of this Rayleigh dissipation function. This is only working for forces that are frictional forces that are like this. If you look at the literature, there are of course frictional forces that are much more complicated than the ones that you see here on the screen. Okay, so now we arrive at the third formulation of Lagrange, and maybe it's not the one that is used most often. Very often frictional forces in first instance are kind of forgotten. Then you derive the equations and you add the frictional forces in your differential equations that you have, for instance, obtained using the second formulation. But it's possible to use this third formulation of Lagrange, and the difference comes from this term over here, right? This is Rayleigh's dissipation function, and you take the derivative with respect to the derivative of the generalized coordinate, right? L is still the Lagrangian, so it's K minus U, kinetic energy minus potential energy, and here this Qj is again a generalized force. Okay, remember that in general you have n bodies, n particles, so you have a sum of n here. Okay, but in this generalized force you take into account, of course, external forces. They are not taken into account by the potential energy or Rayleigh's dissipation function, and more complicated friction forces, the ones that cannot be written as the gradient of some dissipation function, right? But in most examples, what you will have here now in the generalized force is only external forces. Remember that this dissipation function is written over here. Okay, let's go to our very simple spring damper mass system on an inclined plane, and remember that we can describe the motion in terms of this generalized coordinate q. Okay, so this is most of the things that you see here on the slide you already know. The kinetic energy, well, you can write it as a function of q dot squared. You can write also the potential energy. This is the potential energy stored in the spring, and this is the potential energy coming from gravity, right? Lagrangian is simply the difference between kinetic energy and potential energy, so you obtain this thing here. And Rayleigh's dissipation function in this case is very simple. It's a half cq dot squared, right? So we are now ready to apply the formula. Okay, let's have a look at our third formulation of the Lagrange equation. The only difference comes from this term, which is Rayleigh's dissipation function, and in our case here Rayleigh's dissipation function is simply a half c q dot squared, right? This thing here, we know that previously it was qc, but now this qc is taken into consideration by this term here. So in this case, since there are no external forces, the generalized force in this formulation of the Lagrange equation will be 0, right? If we would have an external force, we would have something different from 0 here. Okay, so this gives you 0. We had already computed this term and this term, right, previously. This one is over here, and this one is over here, right? So now we need to take the derivative of this one with respect to q dot. Okay, so again we have to see this thing here, q dot, as a variable, right? And this gives you this formulation, right? And now writing down the equation, well, you obtain exactly what you had obtained previously for formulation 1 and 2 of the Lagrange equation. Okay, so now we have seen the Lagrangian formulation. We have seen 3 formulations. We can kind of look at what are the advantages of this formulation. Well, you only work with scalar functions, which are the kinetic energy, the potential energy, and the dissipation function. And this is kind of simplifying the problem, because you can write these quantities in terms of the generalized coordinates, right? And if it's not possible, you write them down in terms of the Cartesian coordinates, and you use the transformation equations. The number of equations is always equal to the number of generalized coordinates. It's always equal to the number of degrees of freedom that you have in your system. Okay, and of course generalized coordinates often do not coincide with Cartesian coordinates. The advantage of these generalized coordinates is they are linked to the degrees of freedom. And an additional advantage is that the linking forces never enter into the picture of the Lagrangian formalism, yes. And you see that in this Newtonian approach, at least the very formal one, you have these linking forces from one body to another that have to be eliminated. And as I said, this is very tedious, especially for systems with a lot of bodies. Okay, let's take a slightly more complicated example, which is the pendulum on cart system. And I will try to prepare things here on this slide. Remember that we had 2 generalized coordinates, which are q1, which is x, the degree of freedom of the cart, and q2, which is phi, the degree of freedom of the pendulum. Okay, so I will now try to write down things for you. The first thing that we need is the kinetic energy. Well, you have the translational kinetic energy, so that will be of the cart, and so this is half the position, the mass of the cart times x dot squared, right? Then you have the pendulum, but the pendulum is turning around the center of mass. Okay, so there will be rotation, but there is also translation, right? So we'll first write the term in rotation, a half, then the moment of inertia around the center of mass times phi dot squared, plus you have here a certain velocity vector, which we'll call VCM. And this velocity vector, well, if you take its norm, it will give you the speed. So we need to write a term for translational energy. Yeah, so this is now linked to the mass of the rod times VCM squared. So this is the velocity vector. If you take its magnitude, you obtain a speed. I have now the kinetic energy. So how are we going to obtain this one? Well, you need first to write the position vector of the center of mass, which is x plus L rod sine phi, and L rod cosine phi. Okay, if you have this one, you can write the velocity vector by taking derivatives, right? And if you have this one, you can take its magnitude, and this will be VCM. Okay, so this will be the procedure that we'll be following. We need two other things here. Write it down over here. It's the potential energy. Okay, and when we talk about potential energy, well, here it's potential energy that is related to gravity. We had already done something similar for the pendulum at the very beginning of the course when we started talking about energy, and we can write it like that: m rod times g times L rod times 1 minus cosine phi. The interpretation is that when phi is equal to 0, the potential energy is 0, it's at its minimum, and when this one is equal to pi, okay, 1 minus minus 1, you'll have 2 times this here, and the potential energy is at its maximum. You remember that potential energy is defined up to a constant, and you see here that there is something constant here in front. So instead of using this expression here, I will write down the potential energy as m rod g L rod cosine phi with a minus sign in front. Okay, so the constant has disappeared. You know that in the Lagrange equation you take derivatives, right? So this constant term will disappear anyway, and another interpretation is that potential energy is always defined up to a constant. Okay, so now I still need this Rayleigh dissipation function. I see dissipation over here and over here, so I will have two terms, one related to translation, Cx x dot squared plus a half C phi dot squared. Okay, so here is my Rayleigh dissipation function, here is my potential energy, and here you have the kinetic energy, where we will have to do the calculation here of the speed at this point here. Okay, so this is the kinetic energy, and as I was saying, you have a term for the cart due to translation, one for the pendulum due to translation, and one for the pendulum due to rotation. We're now going to spend some time on computing this term over here. Okay, so here what I want to compute is this thing here, so it's the speed squared, right? So it's a half, and because we want the kinetic energy, a half m rod VCM squared. Okay, so this is why we need this one. How do we proceed? We write the position vector of the center of mass, and I'll write it like that, YCM, and then you can of course obtain the velocity vector of the center of mass, and I will use these notations. Okay, going from here to here, it's simply taking the time derivative, right? You plug in these values and these values in here, and you obtain the velocity vector. I'm interested in the speed, VCM. Well, that's simply taking your velocity vector and taking the magnitude, right? So VCM squared is this one squared plus this one squared. You've got it here. you do the maths and you obtain this thing here. Right now you're in a position to compute a half m rod VCM square. You'll have three terms, one related to x1 x dot squared, one related to this term here, and one related to this term here. The 2.5 will compensate each other. Okay, so here's the kinetic energy, okay, written in full. You have here a half mass of the card times x dot squared. That's the kinetic energy related to the translational energy, kinetic energy of the card. You have the rotation energy of the pendulum, okay, and the three other terms, right? This one here times m rod, this one here, and this one here. It's related to the translational energy of the rod, right? So now we have our kinetic energy, we have our potential energy. Don't forget that we have left out this constant, because potential energy is defined up to a constant. We have also our Rayleigh dissipation function, and the Lagrangian is simply the difference kinetic minus potential energy, and you obtain this function for the Lagrangian. So let's now apply the Lagrange method, and since we have two bodies, well, there will be two Lagrange equations, one related to each of the generalized coordinate, the first one being x and the second one being phi. So if I specialize my Lagrange equation to x, this is what we obtain, right? We need to compute the partial derivative of the Rayleigh function with respect to x dot. There were two terms, right? F was a half cx x1 squared plus a half c phi dot squared. Okay, so if I take the derivative with respect to x, this is what I will be obtaining, right? So next I need to go to my Lagrangian and take the derivative with respect to x and to x dot. So what I will do is go back. You see here the Lagrangian. You see that there is no contribution with respect to x, so the partial derivative with respect to x will be 0. And if I take the Lagrangian and look at the dependence to x dot, you have this thing here and you have this thing here. So taking partial derivatives, I'll have total mass times x dot, and then I'll have this term to take the derivative with respect to x dot. This will not give a term, right? If I take the derivative with respect to x dot, this thing will disappear. I'll have m rod L rod cos phi times phi dot. So this is exactly what I have obtained over here. Yeah, the 0, the term that I've just seen here, and now in my Lagrange equation I need to take the time derivative of this thing here. This is easy, right? And this is a little bit more complicated, but not that complicated, because here you have the product of two things, and so you'll have two terms, right? So this is this term. This term is producing 0, and this one is producing this thing here. Okay, so you have, if you take both of them, right, this term here, and on the other side of the equation you have the generalized force in the direction of x, and we will show later that this is equal to the force that is applied to Descartes. Okay, so now I write the Lagrange equation, but specialized for the second generalized coordinate. Okay, so this is what we are writing then. And again, I know that this dissipation function is a half cx x1 x dot squared plus a half c phi dot squared, taking the derivative with respect to phi dot. So it's taking really the derivative with respect to phi dot. So phi dot is a variable. I obtain this thing here, right? So now I need to go to my Lagrangian and take the derivative with respect to phi and the derivative with respect to phi dot. I need to go back 2 slides. Here is my Lagrangian. So if I take the derivative with respect to phi, there is only one term that depends on phi, so I'll have this thing here times this thing here times the derivative of this one, right? So that will give me a minus sine phi, right? I don't want to see any phi dot over there, because you take the derivative with respect to phi. This is a mistake that is often made, right? So let's now look at the derivative with respect to phi dot, and again you have to see phi dot as a variable. Of course, this term will give a contribution, this term will give a contribution, and you have phi dot over here. Okay, so you expect to see 3 terms in this derivative. This is indeed what you see, right? This is this derivative of the Lagrange with respect to phi. Yeah, this minus and sine phi appearing, and here are the 3 terms that are coming from the derivative of the Lagrange with respect to phi dot, right? If you now write this equation, this is what you obtained. It's simply doing the math, and this generalized force, right, in the phi direction here will be 0. Okay, I will be showing that next. Okay, the last thing that I have to do for this pendulum on card example is that we need to have a look at these generalized forces that were appearing in the 2 Lagrange equations, one for the generalized coordinate x and the other one for the generalized coordinate phi, right? So the formula of the Lagrange or the generalized force is this one here. Okay, so you have to go and have a look at the definition, and for that you need the position vector of the 2 bodies, right? For the first body it's quite simple, it's as a function of course of the generalized coordinates, and for the second body you have this thing here. This is something we had already seen before. So now in our generalized forces we have to take only external forces, because we remember that friction forces have been taken into account in the dissipation function. So on body 1 there is a force acting, right? And it's in the direction of x, so we'll write it down like that. And on the second body there is no force acting, so we'll write it down like this, right? So if we take the partial derivative of r1 position vector with respect to x, it gives me a vector, and this vector will be simply 1, 0. Okay, and if I take the scalar product with this one, it will produce me f, right? These terms here that will produce 0, okay, because of this here, and this term will produce a 0 also because the derivative of this one with respect to phi is of course 0, okay, so this one is not going to contribute. So indeed the generalized force, when I was considering my generalized coordinates x, was indeed F, and the generalized force when my application of the Lagrange equation for the generalized coordinates phi was indeed 0. Okay, so this concludes this example on the pendulum on card. This also concludes the presentation with slides in this second part on the course. On this first part of the course on Newtonian and Lagrangian mechanics. I will be adding another video with the application of Lagrangian mechanics to examples.